This is the second lecture in our Chapter 3 Modern Chemistry text. In this lecture, we're looking at how we can measure atoms, ways that they can be described, and calculations that can be done in terms of numbers of atoms and characteristic properties of individual atoms. So the first way that atoms are defined or characterized is by the number of protons that they have. You might remember from the last lecture, every element has a unique number of protons. That number is called the atomic number, and it is used to organize the periodic table. It's one of the ways, actually, I should say, that the periodic table is organized. Hydrogen has an atomic number of 1, and it's the first element on the periodic table. Helium has an atomic number of 2, and then we go up from there, 3, 4, 5, 6, blah, 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 and in ascending order. So when you look at the periodic table, you'll always be able to see the atomic number. Here's an example for the element nobelium. The atomic number is always indicated, and even if it doesn't say atomic number like this one does here, you can tell what the atomic number is by looking at the elements on either side. The atomic number is just the number that is one more than the one to the left and one less than the one to the right. Another way that we talk about atoms and elements is in terms of atomic mass, and we're going to get to that in just a moment. Interestingly, we've talked a lot about how individual atoms are unique to the element. Every element has the same kinds of atoms. But what we haven't talked about is that even though the atoms of each element are the same in terms of protons, there is some variation from atom to atom. And often that variation is in terms of the number of neutrons. So the nucleus can be slightly different from one atom of, say, hydrogen to another atom of hydrogen. It will always have the same number of protons. It will always have just one proton. But the hydrogen atom might have a different number of neutrons, which causes there to be some variation and some difference in the ways that the atoms behave sometimes. So these different versions of one type of element are called isotopes. So to stick with our hydrogen example, there are 3 isotopes of hydrogen. Usually they don't have different names, but in hydrogen's case, each isotope has its own name. So protium is the isotope that has just 1 proton and 0 neutrons. Because we know that the elements have to be balanced, right? If there's 1 proton, there's always going to be 1 electron. The second isotope is deuterium, and in this case, there's 1 proton, 1 neutron, and 1 electron, so 1 of each. The last type is tritium, 1 proton, 2 neutrons, and again, 1 electron. So in this case, we see some examples of a really simple atom and the ways that the subatomic particles can vary. The information about isotopes is really important because the different isotopes of an element will have a different mass. Because there's a different number of neutrons, and neutrons are the heaviest of the 3 subatomic particles, if you take out a neutron or add a neutron, it can have a pretty dramatic effect on the overall mass of that atom. Sometimes you'll hear our text will also refer to isotopes as a nuclide. It might say, these are the 3 nuclides of hydrogen, which just means the 3 versions of isotopes. A lot of times we will just write the name of the element, hydrogen, and then the number of the isotope, and the number of the isotope is determined by the total mass number, which, as you hopefully remember, is the number of protons plus the number of neutrons. That's how we get the mass number for an atom. A lot of times you'll also see the nuclear symbol. So the atomic symbol for hydrogen is H, usually with a 1 to represent that it has 1 proton. When we are showing isotopes, what generally will happen is we'll have the atomic number down here on the left-hand side in a subscript, and we'll have the mass number up above it. So you can see that this would be an isotope of tritium, Deuterium would have, again, 1 proton and a mass number of 2. And the typical hydrogen atom has 1 proton and a mass number of 1, because hydrogen is a very strange little element and it has no neutrons in its most common isotope. So those are examples of nuclear symbol. They just include the the elemental symbol, right, the shorthand version. It includes the mass number and it includes the atomic number. And we'll work more with this going forward. We also use the differences in mass number dependent upon the isotope that we're looking at in order to determine the relative mass of an atom. Because atoms are so tiny comparatively to everything else on Earth, it's a really hard number to kind of work with. The relative mass of an atom is somewhere in the neighborhood of 1 times 10 to the negative 23rd. This, darn it, my little program again dropped off my exponent. So there we go. That should be 10 to the negative 23rd, which is incredibly tiny. So what scientists have done is to come up with a new standard that is an easier number to work with. And the unit for this new standard is called the atomic mass unit, or often we just say the AMU. And arbitrarily, the scientists decided that this unit would be set based on carbon. So they said, because carbon has an atomic number of 12, it has 12 protons, we're going to say that carbon has a relative mass of 12 AMUs. So the atomic number in this case is the same as the atomic mass unit for this atom. And so what scientists can do is compare all other elements to how much bigger they are than carbon or how much smaller they are than carbon in the unit atomic mass units. Because most elements, this should have an S, most elements, occur naturally as a variety of isotopes. For instance, tin has 10 different versions. We have to take into account all of the different versions when deciding how heavy the average atomic mass is for tin. This would be kind of like if somebody asked, what is the average mass of a junior? We would have to take the masses of every student in the junior class, add it all together, and then divide by the total number of students so that you get an average atomic mass. It accounts for every single person. And in the average atomic mass of an element on the periodic table, we do the same thing. We account for all of the different isotopes and how much each of those isotopes weighs, and then how common that isotope is, and then we use that to determine the average atomic mass. That's the number that you see on the periodic table as the mass number. There are some other units that we will use quite frequently in chemistry, and the first one is the mole. And this is a totally bizarre unit name, but it comes from molecule or molecular. And so mole is the primary unit for measuring numbers of atoms, although moles can be used to measure the number of anythings. It is just a comparative or a relative unit, something like a dozen, right? A dozen donuts is 12 donuts. A dozen cars is 12 cars. A dozen roses is 12 roses. Moles are the same thing, and moles just represent the number of particles that could be found in 12 grams of carbon, okay, which is, again, a pretty arbitrary measurement. So what has happened is a lovely Italian gentleman named Amedeo Avogadro, who spent most of his professional life dedicated to studying atoms and numbers of atoms and things like that. He developed a constant, which we now call Avogadro's number, that represents how many particles this would be. Since we don't have at our disposal a way to calculate the number of carbons in carbon atoms in a mass of carbon, Avogadro has developed this constant that says that 1 mole is equal to 6.022 times 10 to the 23rd anythings. So 1 mole of carbon is 6.022 times 10 to the 23rd atoms of carbon. 1 mole of humans would be 6.022 times 10 to the 23rd humans. You can see that is an exceptionally large number. Because atoms are so tiny, it takes tons of them, in fact, 6.022 times 10 to the 23rd of them, to make up 1 mole. This is useful to us because we often compare things in terms of molar mass. We say, how much of this substance do I have? And in order to do that, we have to know what the substance weighs all by itself when it's a pure substance in nature, and then we need to find out how much it weighs in real life. How much does the sample you have in your hand actually weigh? So we need a way to compare the number of atoms, which is where we get our mass from, with the number of grams or whatever we have in our possession. So we use a value called the molar mass in order to do this. And what this value represents is that 1 mole of anything, let's say 1 mole of water, is equal to the mass of the component parts of that substance. So in this case, 1 mole of water is equal to however much 2 hydrogens plus 1 oxygen weigh in AMUs. And so that gives us a way to easily convert from real-time units like grams into hypothetical or theoretical units such as moles, which is pretty handy because it's very difficult to not only see the number of atoms you're dealing with, but to find some way to reasonably measure them. And that's what we've done with molar mass. Pretty abstract concepts, and they're a little bit hard to visualize. The way that we are going to work with them, there are some sample problems in your book. There are 4, and they're really nicely laid out. They're basically conversions, and we are using what you've learned with unit analysis, and we're converting from laboratory measurements of things like grams, for instance, to theoretical measures of things like moles. And you can kind of get some practice at how to do that. The book also explains exactly how to solve each of these problems. We're going to go over them again in class, but I would really like you to look those over so you have some questions for me. So that's what we're going to do this time. Any discussion questions you have are great. If you don't have any off the top of your head, then you need to have some related to these sample problems, some clarifying questions or calculating questions or something like that. And I will see you in class.